Hi, this is Mrs. Evans, and before we go on with limits, I wanted to spend a little time with you around a calculus vocabulary term called indeterminate. Indeterminate is going to come up quite a bit when we start working with limits and when we deal with rational functions. So we're going to talk real quick about a rational expression. When you were younger and you learned about rational numbers, or ratios, they were basically fractions. When you get a little higher up into math, rational expressions actually have polynomial expressions on the top and polynomial expressions on the bottom. They can be really simple, like 5 over x, or x over x plus 1, or they could be as elaborate as what I have to the right here. I have a trinomial in the numerator and a trinomial in the denominator. Well, the difference is that polynomial expressions are really easy to graph. They're continuous, they're smooth, they don't have any sharp turns, and they don't have any holes. But when you put a polynomial expression in the numerator and a polynomial expression in the denominator to form a rational expression, all kinds of things can happen. You can have a vertical asymptote, you can have a horizontal asymptote, a slant asymptote, or even a hole. And these aren't usually very easy to graph. However, we'll spend some time in another course for calculus that actually gives you the opportunity to graph these to really understand what's happening utilizing calculus. For now, though, we're going to go back and just talk about some of the simple rational expressions that you learned when you were younger. Well, we learned how to divide 6 divided by 3, and we learned that we could put it in a fraction form. Well, in this case, we can prove that 6 divided by 3 is definitely equal to 2 by saying if I take 3 and multiply it by 2, I get 6. That's actually a little bit of a proof that you can use to prove that fraction has the answer of 2. Well, what happens when we have 6 divided by 0? So think about that for a minute. When you're trying to decide what the answer is, you can always go backwards and say to yourself, 0 times what number gives me 6? Well, what number times 0 gives you 6? There is no number. I can think of no number that I can multiply by 0 to get anything. So this is undefined. There is no definition for this answer. There is no answer. And when you're talking about a graph, when you're looking at a graph, when you have a point where it's undefined, you might have a vertical asymptote. Well, what about 0 divided by 0? What could I multiply by 0 to actually get 0? Is that undefined? Well, when I think about it, I could actually put 5 in there. If I went 0 times 5, I'd get 0. So that works. I could put in negative 1/3. 0 times negative 1/3 gives me 0. I could put in 3 million. 3 million times 0 gives me 0. I could even put in something as crazy as the cube root of 7.5. 0 times the cube root of 7.5 is 0. So is this really undefined? Does that mean there is no answer? To me, it looks like there's lots of possibilities. Well, in this case, this is actually indeterminate. What this means is there is an answer, but we just don't know what it is yet. And that's a lot about what's going to happen in calculus. We're going to figure out what is that missing number. So, as we talk about this with limits, let me give you a couple of examples. Let's just look at this rational expression. I have a polynomial expression on top and a polynomial expression on the bottom. I want to know what is the limit as x approaches 3. Well, what you're going to learn is you always want to try direct substitution first. So I'm going to substitute 3 in for x here and 3 in for x here. And when I do that, I get 3 plus 2 on top and 3 plus 3 on the bottom, or I get an answer of 5/6. So the limit as x approaches 3 is 5 over 6, or 5/6. Well, what does that actually mean? Well, let's think about that graphically. Look at the graph over here. This graph is the graph of x plus 2 over x plus 3. Now, it looks like something really funny is happening around here. Looks like my graph goes up to infinity, and then from here it comes from negative infinity and comes back up and flattens out a little bit. And most people look at this and they say, oh look, my calculator graphed a vertical asymptote for me. Well, there is a vertical asymptote right there. That's a spot that is undefined in the graph that we cannot cross. However, the calculator is not actually graphing that for us. The calculator is actually connecting the last point on the left to the first point on the right, and it's actually drawing a line. But it's kind of nice because it looks like it's doing an asymptote for us. But what's cool about limits is I really don't care about what's happening right here. What do I care about? I care about what's happening close to 3. So here's 3. 1, 2, 3. I want to look to see, as my x value is approaching 3, what is my y value approaching? Well, according to this graph, it looks like it's close to 1, but not quite 1. So does it make sense that the answer could be 5/6? I went ahead and put this in a table also. When I put this in the table, I plugged in 3 into the function, and I got 0.833 out as my answer. That's my y value. And the limit as x approaches 3 is the same from the left as it is from the right. So that's my answer. And so here's one of the things that comes up. When you're doing the limit of a rational expression, sometimes you get an answer and you're done. Well, let's look at another case. This is the exact same rational expression, except for I am looking at now what's happening as x approaches -3. What's the limit? Well, we're going to put in -3. We're going to use direct substitution. When I put in -3, I get -3 plus 2 over -3 plus 3, which is actually -1 divided by 0. Now think about what we talked about last time. Can I multiply anything by 0 to get -1? No, there's no way possible. That is undefined. Well, what does that look like graphically? Well, graphically, coming back over this exact same graph we had before, now we're looking in this area. Well, graphically, I have a vertical asymptote. So when you get a non-zero number on top for your answer and 0 on the bottom, what's happening is you're going to be running into a vertical asymptote. So you're basically finished. What you can say is the limit as x approaches -3 does not exist, because as you learned earlier, if it's going to infinity, there is no limit. And it also breaks the law of it's not doing the same thing coming from the left as it is coming from the right, because they're actually one's going to positive infinity and one's going to negative infinity. Some people might say that the answer does not exist because it's approaching negative infinity and positive infinity, but just saying the limit does not exist is enough in this case. Now let's look at another example. This example isn't the same function, it's a little bit different. But we're going to use direct substitution just like we did before. And if I plug in a -3, I have to go -3 squared minus 9 and -3 plus 3. -3 squared minus 9 is 9 minus 9, which is 0. And -3 plus 3 is 0. So I get 0 over 0. Well, if you'll remember from what I taught you a little bit earlier, is this could be just basically any answer. 0 times 800 could be 0. I have no idea what the answer is. Well, let's look at this graphically. When you look at this graphically, what's weird is I have a line. Could you imagine that this ugly function would actually come out to look just like a line? I wonder how that's happening. Is it exactly a line? It looks like it might be the line y equals x minus 3, because it looks like it crosses at -3 and goes up 1 over 1. So my guess is it's the line y equals x minus 3. But is it exactly the same as that line? Well, what you'll notice if you do the table is that when you put in the numbers, your y value is approaching -6 right here, but exactly at -3, there's an error. That means it can't have anything there. And I can't zoom in well enough, but if I did, I would see a little hole right there. So in this case, I don't have an asymptote, but there's a hole in my graph instead. The hole is at -3, and the y value of that hole would have been -6. Now, you may wonder, how the heck am I ever going to know that by looking at that ugly graph? Well, that's what you're going to learn coming up in some of the future videos. Hopefully, by the time the videos are over with, you'll understand how to find the answer to this problem.